Okay. Hello, people. I'm Rushil. I've been asked to take this class on probabilistic method very unwillingly because I am not a believer in anything except soft techniques anymore. But I will teach you guys probabilistic method. Um, oh wait, that is not the right way to write. Yeah, probabilistic. Can I spell it? I think I can. There we go. Okay. So what do people understand from this? Also feel free to like turn on cameras, talk during class. Like I'm not done this for a very long time, and so I've gotten bored of just like talking. So it'll be fun if people speak up because then it's something new for me. This is not like my definition of people talking up, but like okay. Um, Come on. Surely someone here has heard of the probabilistic method. Oh, are you expecting me to read chat? Is that it? A method which is probabilistic. Wow. Um, EV scam. This is one of the misconceptions, in my opinion, that things are EV. You choose randomly some stuff. Oh, okay. That Korea problem with C8 Summit. Okay, bro. Um, Chapter 16. Is it 16? I thought it's 15. Maybe it is 16. I mean, you probably know. So the right answer is, of course, chapter 16. There's no other answer. Probabilistic method is, in my opinion, a way of um, sort of showing existence of things without constructing. And it's one of the few methods that gives you such uh, abilities to do something like this. Because generally, let's say a problem asks you to prove, let's say, prove that there exists um, like n people, all of whom, blah, 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 blah. And the proof that, you would generally do is like, okay, fair enough. I will, let's say, take the first person as this person, second person as this person, until the nth person as this person. Um, And that's inherently a very constructive method where you are explicitly defining it and then you're proving that those n people have that property. The thing that probabilistic method often gives us is that it gives us an existence result. It tells us that there do exist n people with these properties, but it tells us nothing about which n people you should choose. Rather, it says that even if you just pick them randomly, they will probably work. Like essentially it's a way of like almost joking at the problem statement, saying that like what you're saying is like just expected to happen. That is literally the exact this thing that probabilistic says, that if I literally didn't even think about the people I picked, or I thought about it very little, like let's say I just decided that each person is likely to be picked with a fixed certain probability, then things are going to work out. So it's inherently a very interesting method because and this is why it comes up a lot in college mathematics as well. Although I'm not a big fan of it in college math. I don't know. It just seems quite boring to me. But at least at an Olympiad stage, it's a lot of fun. Um, and the reason people really like thinking about it is because it gives these deep abstract results which are not easy to prove without it, because you may not be able to always construct count examples or examples. Okay, but that's enough. Yeah. So let's break this down. I think the first misconception, forget misconceptions about probabilistic method. There are misconceptions about the word probability itself. Um, so what is probability? That's an interesting question to think about. And um, maybe a bit of like the history of how probability began. Probability is a measure. Yeah, yeah, yeah. That's the right answer, to be fair. Actually, I have a course on measure theory right now, so I'm finally learning it officially. Um, but they're going quite slow. Okay, anyway, so probability is okay. Let's go back a bit about the history of probability. So there were these random people playing a game of, I think, poker or some card game, like where they had like bet a lot of money. And unfortunately, in those days, wherever they were playing, like this sort of gambling was not permitted. So the police came in and they stopped them. How late are you? You're not very late. I've not said much. You can just listen on. So there are this police and they've stopped these people from finishing their game of poker, but the money is in the middle. So who? Okay, I am back. I was very scared because the this could have been a lot worse. Net here has had some issue. Like there was a power cut yesterday, and then everyone lost eduroam. Uh, but it seems this was not related to that, so that's good. I will start sharing again. How does one share screen again? What?
The rumor is that FBI had come to get you because you were gambling. Oh no.
Yet again.
The SDI is in US.
This is unfortunate.
Hi. Wait.
I
Let
am,
me give you host permissions.
no,
Oh,
no,
you
I
are
think I
already.
can
Okay.
share. Yeah. Okay, fine. Hopefully that was the end of all of these issues. If not, so be it. Um, okay. So where were we? That there's this police argument, etc. And then the definition of probability that sort of came up in that time is essentially that like it's the number of favorable outcomes by total number of outcomes, which is like um what also is taught in CBSE. And it's a wonderful definition, but it's not correct, unfortunately. Um, what do I mean it's not correct though? It's a definition. Definitions can't be right or wrong. Maybe the right word to use rather than it being right or wrong is that it's not a very useful definition, because it fails very easily. It is a useful way to think about probability though. Um, so um, much slightly, what people like to do a lot in college math and in general in advanced math is think about properties of a certain object. And then instead of defining the object first and then showing that it has those properties, they say we define this object to be any object that has these properties, and that's the definition. So essentially, probability definitely should satisfy these basic things, like, okay, probability of like of nothing should be zero. Like probability of like if you, let's say there are n things that can happen, a1, a2 till an, the probability of um whatever, like there are these things like this, and then probability of, if a1 and a2 are disjoint, then the probability should add up. You have these random axioms like this, and then the point is you like extend beyond. But this is still like not really telling us what probability is. Probability is inherently a function. So the right way to think about probability is as a function from some set of possibilities. So it's a function from some set to like real numbers. In fact, real numbers which are between 0 and 1, because probability is always between 0 and 1. And so there are some possibilities of what's going to happen, and each of them is mapped to a probability which is between 0 and 1. And there are some rules, like the sum of everything should be 1, etc., etc. Yeah. So the thing is that when you say that the probability that a fair dice rolls 1/6, the rolls 1 is 1/6, it's not because there are 6 possibilities and this is one of them. It's because we defined it to be 1/6 for a fair die. It's a function. So you have inherently defined what the probability is for each of those events. Um, and so it's the right way to think about this is you have defined the probability already, that it's not something you ever calculate. Probabilities are never, I mean, you can calculate, let's say, the probability that you roll an even number as the sum of the probabilities of 2, 4, and 6. But inherently, these are all coming out of what you defined, not out of something else. Um, and yeah, people are talking about things like, you have probabilities over spaces which are not like finite. Of course, you could have like a probability like let's say it takes any number between 0 and 1 with equal probability, the uniform distribution on 0, 1. And then the probability of getting any single number is 0, because like there are so many. I mean, that's at least the intuitive way to think about it. Of course, it could be more formal than that. But then you have to define more formally how a continuous random variable, etc., would look like. Um, but yeah, so I mentioned an interesting word here, which is a random variable. A random variable is also a function. And the thing with probabilities was that they always get mapped to 0, 1. You want to sort of lose this necessity. So a random variable also maps all your possibilities to some set. But that set need not be 0, 1. Generally speaking, it's like some real numbers, but it may not be this. You can have a random variable whose outputs are graphs, or a random variable whose outputs are like sets, or like anything. But for most of our purpose, random variables will generally take real values. And the reason we would generally like to do this is because then we can reason about the expected value of the random variable. Um, and uh, I guess in some cases, even when it's not a real number, you can still talk about the expected value. At least, for example, if it's a complex number, you can for sure. But yeah, you have to be a bit careful in general. Um, so anyway, why we're talking about all this is that essentially how probabilistic method proofs look like. Like, let's say you want to prove there exist n people. One common technique to proving something like this is, let's say I don't know, there were 1,000 people originally, and you need to show that there are 20 people with some property. And now the proof will essentially look like, okay, let's say we pick a random subset of 20 people. And then we check how many of these people are good in the sense that like we need 20 people who are all good, as in 20 people who all satisfy a required property or something. But maybe that's not true. Maybe only 18 of them will satisfy the required property. Um, so you essentially look at the random variable x that represents the number of people that are good. So essentially, the set of possibilities is the set of people we choose, and each of them is equally likely because we said we uniformly pick among those 1,000 people, we uniformly pick a set of 20 people. Um, and then each of those possibilities maps to some real number, in fact, an integer from 0 to 20, which would represent the number of people who are good. And if we can show that the average value, and that's more commonly known as the expected value of this random variable, if we can show that this is like 19.1, let's say, which is a very strong statement, it means that if there was no place where all 20 of them were good, then the expected value should be at most 19, because inherently we have not yet defined what the expected value is, but at least thinking about it as the average value, um, if the average value is like 19.1, then you can't always be below 19. So it's inherently this mix of, you're using this probability argument, but you will also be using at some point this pigeonhole argument, which is that if everything is, uh, if there's something, at least something, then whatever. Like the same thing holds in pigeonhole. Like if you have n plus 1 pigeons and n holes, then the average number of holes per pigeon is 1 plus 1 over n. So there is some hole which has two pigeons, because if all had at most one, then the average can't be more than one. It's inherently the same idea. So that's enough of like understanding, confusion, etc. Let's talk about something real. So we'll actually not even talk about expected values yet. We will just talk about probabilities. And we will talk about one very, very simple thing about probabilities, which is that if you have two things, A1 and A2, the probability of this union is at most the sum of the individual probabilities. Surely everyone agrees with this, right? Like let's say the question is you're rolling 1 or 3 is event 1, event 2 is 3 or 5. Surely the probability that you roll 1, 3, or 5 is at most the sum of these probabilities. In fact, it will not be equal if the probability of rolling 3 is not 0. Um, but this is surely true. And in general, you can put n of these here and put n of these here. Um, So if I have like this and union A3, union AN, and this is generally known as the union bound. And this is one of those, things that is totally obvious, yet incredibly useful. In fact, you can do at least half of the probabilistic method questions by just thinking about this. Even though people don't actually do it. People generally think of expected values directly, but they really don't need to. This is generally good enough, and it's strangely useful. Um, so let's look at a real example. So along the lines of what I was saying in theory, let's say there are 120 people, and this is a very common example, so some people might have seen it, but it's okay. You get to see it again. 120 people, okay, sorry, 200 people are giving, let's say, the IMO, and at least 120 people solved each of P1, solved P1, at least 120 solved P2, um, and so on. So at least 120 people solved each of the 6 problems on the exam. And you want to show that there are 2 people who have together solved all the problems. And this is interesting because, like the first thought you might have is that, um, yeah, this one is probably there everywhere. It's like a very well-known example. I just think this is a good way to start just because it's quite straightforward and clean. Because the other examples are going to become less and less clean. Okay. So the thing, so yeah, this was also in my book, and the thing that I was almost about to write when I was writing my book is that um, there's this inherent difficulty in this problem that you don't know how to choose two people. Like, how will you choose them? There's no logical way of doing that, except maybe pick the person who solved the most problems, but then it's confusing, right? And I turned out to be wrong because I decided to do a class before I published my book. And I think this problem came up. And someone actually gave me a solution where you just start by picking the person who solved the most problems. And the observation is that how many problems must this have been? Let's say it was um, k problems. Then you're saying that all people solved at most k problems. So at most 200 times k problems were solved overall. But you know exactly, no, at least 720 problems were solved. Like 720 solves happened because there was 120 solves on each of these. Um, so inherently, you know that k is at least 4. Because if k was 3, then it's at most 600, but at least 720. That's absurd. So there's one guy who has solved 4 problems, which without loss of generality, let's just say at P1 to P4. I guess P5, P6, he just got bored. Um, so anyway, P5 and P6 are left, and now you want to show that there's someone who has solved them both. Someone who has solved both P5 and P6. And this is also quite clean because let's say each person has solved at most one of these. Then the number of solves that happened on P5 and P6 is at most 200 because there's at most one on each of these. Like if there are 200 people like this, each of them contributed at most one solve. So there are at most 200 solves. But we know that there are 240 solves on P5 and P6. So in fact, we are done already. Um, so I had to unfortunately delete this line from my book, which is that there is this inherent difficulty that you cannot do it without like using probabilistic. You can. But it is also true that still thinking about probabilistic method, and this is a good idea in terms of understanding how things might work, especially when you can't do it without probabilistic. Yeah, I did end up stating that there's a greedy-ish solution, I think, which was where I was referring to this. Um, and the trick with the probabilistic solution is okay, pick two people literally at random. They could even be the same person. If they're the same person, then just add any extra person later. If like they were both the same person, but pick literally any two random people and check how many problems they solve together. Um, well, the probability that, let's say, the first person I picked, and here's an interesting thing, right? You can think of your random variable as a person as well. Um, although that's a bit silly because uh, you don't need to do that or whatever. But anyway, the probability, let's say the two people you picked are X and Y, and these are inherently random variables um, because like they can take different values and based on different events that let's say the event is I picked person number 7 and the random variable X becomes person number 7. So it's kind of silly to think of it that way. And it might also be confusing, but I think it might start making sense. Eventually, it's not very important. You don't need to overthink it. Um, we're looking to check the probability that neither um, X nor Y, where X and Y are the two people we picked randomly, solved P1. And here it's important that X and Y have been picked independently. So um, it's not like X and Y are always the same because then this argument will fail. Um, and the point here is that the probability is what will this be? Does someone want to answer? 1 by 80 squared. That sounds suspicious. That sounds very, very low.
80 by 200 square.
80 by 200 squared. Yeah, so the probability that x did not solve P1 is 80 by 100. And the probability that y did not solve is 80 by 100. The reason you can multiply these things is because when you have two things that don't depend on each other, that they're independent events, then you can multiply their probabilities. And that's it's pretty simple fact. It's the same reason, you roll two dice, the probability that both of them give you one is the probability that the first gives you one into the probability that the second gives you one, or something like
I think it's
that.
80
80
by
by 200.
200.
Yes, sorry, I can't write. Okay, whatever. So this is 4 by 25, I think. Um, and so the probability that neither x nor y solved P1 union the probability that neither x nor y solved P2 union neither x nor solved P3 till P6. And now we're going to use our favorite union bound. And we're going to say it's at most the sum of those six probabilities. And so it's at most 6 times 4 over 25. So the probability that x and y have, and this thing is inherently checking, is there a problem that both x and y didn't solve? Because this event would, if this event holds, then these two people have not together solved all of them. If it doesn't hold, that means x and y have together solved all the problems. So what we have got is that probability x and y didn't solve all together is at most 24 by 25. And what this means is the probability that x and y solved altogether is at least 1 over 25. In particular, there is a non-zero probability that they solved all of them. And in general, if some probability is non-zero, then that means that there is some event where it occurs. So there's some choice of x and y for which they did solve all. Because if there was no such pair, then the probability inherently would just be 1. What do you mean in general? Is there some instance where that doesn't occur? Um, yeah, so the point basically is that in general, if there's an event probability, like if there's an event E, an event is basically something happening. Like let's say here the event was that x and y together didn't solve all of them. If the event's probability is not 1, if it's less than 1, then um like so what there were a set of possibilities, right? And some of those possibilities are like favorable in the CBSE sense, and some of those were unfavorable. And so if probability is less than 1, there is some option that's unfavorable, because if everything was favorable, then the probability would just be equal to 1. Um, Wait, but this works even if at least 3 by 5 of people solved each problem. Either will, yes, exactly. So this had nothing to do with the number of people. It just needed the ratio 3:5. Um, yeah. Um, but yeah, this is quite neat. So is it that the other one fails if you change the other solution? I'm wondering maybe that doesn't work if you make these things a lot larger. If you have 300 and 500, does it still work? Uh, Maybe it still works. Yeah, I think the same argument works because the ratios are all that we needed, even in that argument. Um, I think it's, yeah. Okay. Anyway, so yeah, so this is the general approach. You're going to uh, think of some sort of possibility space, show that the probability of some bad thing happening is less than 1. So there's some possibility where a good thing happens. And that's what all you need to prove. You need to prove existence. Um, okay, so let's maybe do. I'm thinking about what's a nice. I guess the famous one again is the Ramsey one. I don't know if I want to do another famous problem. I guess I will give you guys a bonus question for people who have seen all of these things. Um, so we might get to this later on. And this is a very hard problem. Okay, I'll give you two problems then. So one of these problems is that you're given a function from 0, 1 to the n to 0, 1. And you can think of this if you're comfortable with that as f2 to the n to f2. Um, and you define uh, f to be like linear if f of x is essentially um, like uh, okay, I'll just write it out. F of x1 to xn is some ai xi where ai belongs to 0, 1. If this is true, then f is linear. So it's kind of what you expect. Like it's basically this is the equivalent to f being a dot x in the linear algebra world. And yeah, your linear functions are of the form ax plus b in general, but you also need 0 to map to 0 um, for it to be linear in the linear algebra sense. Okay, anyway, so you have this. If this is true, then f is linear. You're given that f of
What is
x plus
x here?
y, what is x?
Yeah, like f
Um,
of x1 up till xn equals ax. But what is x?
so x is the vector x1 to xn, and a is the vector a1 to am. Like
Oh,
you don't need to like I mean this is the definition. This is just something to think of it as it's equivalent to this if you think of dot products of those two vectors. Um, and it's true that if f is linear, then this will hold. Um, Note that addition is a bit tricky. When you add 1 and 1, you think of it as adding to 0. It's kind of like XORing, or it's adding in the mod 2 world, which so that's why this is a slightly better thing to talk about. Um, and so the problem basically is, let's say that the probability that picking x and y randomly at uniformly and independently, whatever. Let's say the probability of this is like 1 minus epsilon. And you have to show that that there is a linear function g. Uh, so f is clearly not linear if the probability is not 1, because for a linear function, the probability would be exactly 1. Here it's not 1. So you have to show there exists g linear such that probability fx equals gx, where x is picked randomly, is at least 1 minus c epsilon for some constant c, independent of n and independent of epsilon. Um, and this is actually a very important and big result in theoretical computer science, actually, because it's a weaker form of what's known as the PCP theorem. And what that says essentially is that if I have a mathematical proof, which might be very long, let's say it's the proof, the Riemann hypothesis, um, I can rewrite that proof in a way that you can just literally check three equalities. Like you pick three things at random, and like let's say it's kind of like you pick three sentences from my proof at random, check that those three sentences are correct, and then if those three sentences are correct, then the entire proof is correct with 99.9% probability. Um, and yeah, so that is quite insane. And this is one of the key ideas in that proof. And at the heart of it is this sort of probabilistic argument, because see here you have to find this g, and in fact, okay, so there's an interesting thing. I saw this problem about 2 weeks back, and and I sent it to Archit, and Archit also sent it to Kevin, who's like, we have some people at Oxford, and so I found one solution which explicitly defines g. um, Kevin found one solution which uses probabilistic method, and that's actually a very beautiful solution. And Archit found a solution which uses some crazy Fourier analysis and linear algebraic techniques. So there are lots of different ways to solve this, but in particular, there's a very cute probabilistic method proof. And the reason why this is sort of surprising is that you're checking something very local. You're picking two random points and checking that equality holds there. And you're able to go to something very global, which is that overall there's a function g which is almost equal to f almost everywhere. So anyway, this is a problem to think about. You can take a screenshot if you want, but I think it's easy to remember. Anyway, now I will go back to doing simple, nice things. Okay, so let's talk about the Ramsey problem, which is also got a funny backstory, which is so you have n people at a party, each pair of whom are either friends or they're not, or they're enemies. Let's say it's a very crazy world where people can't like not be friends or enemies. They're one
People
of
are
them.
asking to go back to the previous slide.
Ah, okay, but like, come on, like, surely you remember this. It's such a clean statement. Um, by the way, if you want to look it up later, this is called the BLR linearity test. But most of the proofs online are Fourier analysis based, which is a bit sad. I think my solution is there online. Um, Bangalore linearity test. No, BLR linearity test. So it's not B for something linearity test. Those are just names of three scientists or whatever. Um, okay, anyway. So the Ramsey problem checks that, so essentially there is this thing that, okay, if you have six people, then there'll be some three that are all friends or that there are all enemies. And this is like sort of a very well studied olympiad problem. And the proof is also quite simple. It's just that, okay, pick this guy. Let's say these three are friends or these three are enemies, one of them. Let's say they're friends. Then these two can't be friends, else you have some three which are all friends. These two also can't be friends. These two also can't be friends. But then these three are enemies. So you always have some three who are all friends or all enemies. Anyway, so in general, it holds that if you just have a very, very large number of people, um, then there'll be some k people who are all friends or some k people who are all enemies. And the minimum such value of n is what we define as rk comma k. You can always define rk comma l as well. There's no reason to just think about k comma k, but it's a bit more well studied. Um, so just to be clear, rk comma k is the minimum number of people you need so that any friendship chart you make on them, there'll be some k who are all friends or some k who are all enemies. And what probabilistic method allows us to do is give us this bound when k is, I think, at least 3 or something. I don't know, some large k, like something like this holds. And this is very interesting. So first of all, it's saying that there's this exponential bound on the number of people you need. And that's a bit surprising at first, but maybe not so surprising. There's been a lot of work on this problem recently. In particular, earlier, the best upper bound was of this order, like 4 to the k something. And I think recently, as in the last 2-3 years, people have pushed this down, I think, to 3 point something. Oh, yeah, there's a Jane Street t-shirt with that bound, yeah. Um, that's quite funny. Is it a Jane Street t-shirt or is it a Ram t-shirt? There's both. Okay, Jane Street. Um, I'm not sure if there's a Ram t-shirt actually. Might be. Okay, Ram doesn't have that. Okay. Um, anyway, I'm not sure what the question is. It's 3.8 something. Okay, whatever. But yeah, so we're going to try and prove this. And inherently, now here's where you really realize that, okay, how are we going to prove this? We need to prove essentially that for 2 to the k by 2 people, I can explicitly construct a friendship chart such that no k are friends and no k are enemies. No k are all friends or all enemies. But I lied. I lied in the sense that you don't have to prove that. You don't have to explicitly construct such a graph. You just need to show that it exists. And that's where probabilistic method comes in, because it's with 2 to the k over 2 people and having to decide every pair whether they're friends or enemies. It's just too much choice. And there's no easy way of choosing them. It's just any construction you give will have some issue with it, probably. It's just the fact that if you have it very random, then it loses those issues. And that's a very weird thing to think about, actually, but it works. So anyway, what you basically argue is, okay, I'm going to, every pair of people, I'm going to randomly decide their friends or their enemies, 50-50% chance. I didn't understand the previous, do we need to find a function? We need to find both. So, okay, so we need to fix a constant. Oh, wait, where did it go? We need to, for a fixed constant c. So first we have to prove that there is a fixed constant c, there exists c positive, um, such that for each choice of such f which satisfies this, there is a linear function which is equal on most things. Does that make sense?
Yes, thank you.
Okay, fine. So yeah, so you literally pick friendships and enemies, these things randomly, and then you check, yeah? So you check what's the probability that some k people turn out to be all friends or turn out to be all enemies. And I mean, that's easy to calculate because there are, each person is friends with probability half. So the probability that all pairs of these k people are friends is half to the power k choose 2. The probability that they're all enemies is also this. So it's 2 times this. And inherently there are n choose k possibilities. Okay, so I won't write that yet. So probability that, let's say, person that 1 to k is bad is this. So a bad 1 to k is bad means that 1 to k are all friends or 1 to k are all enemies. Um, and again, we're using independence here to argue that you can exponentiate correctly. Similarly, probability 1 to k minus 1, but last thing is k plus 1 is bad, is also this. So inherently, for every choice of k people, we have this probability. So the probability that some k are bad is at most by the union bound, the sum of these probabilities. And there are n choose k possibilities for those subsets, and each of them you have this. And now you just do bounding. And I refuse to do it. But basically you put n as 2 to the k over 2 here. And you use some nice things about n choose k. In particular, you use that n choose k is like n to the k by k factorial. Like it's more, it's what? Less than this. Like this holds. And yeah, from there. And I think k factorial, you just use that it's at least 2 to the k minus 1 or something. Like something like this
How
is enough.
when some K are bad?
Sorry?
How will we define
Yeah, so badness is the property that uh, all all of these k things are friends or all of these k things are enemies. So some k are bad is in checking the event that either the first k are all friends or the first k are all enemies, or the last k are all friends or the last k are all enemies, or like the odd indices, some subset of k things are all friends or all enemies. That's the event. And the probability of that, if we do some bounding, we can prove it to be less than 1 when n is 2 to the k over 2. And so there is some positive probability that no subset of k is bad. And in particular, there's no group of k who are all friends or all enemies. Yeah. And yeah, and then you're just done. So that's about the union bound. And union bound is very useful, and it's the first thing you should think about when you're doing probabilities. It's not the only thing you should think about. The other thing to think about is um, expectation. Um, and I'm wondering how badly people want to try that bonus problem. Like, would people be happy to hear that magic probabilistic solution towards the end of this class, actually? Or would people want to try it? What is C? It's some fixed constant you choose. Can you explain last problem again? Sure. Essentially, you want to show that if there are 2 to the k over 2 people, there's some possibility for which no k people are friends and no k people are enemies. Um, how did the 2 come up here? What do you mean? Where is the 2?
And that the probability that 1 comma till k is bad is
2 because all friends or all enemies. So it's like this is like half to the k choose 2 that they're all friends and half to the k choose 2 that they're all enemies.
okay. Yeah.
Yeah. Um, yeah, people would like to try. I understand that. But in my defense, this does have multiple solutions, which are completely disjoint in terms of their ideas. So if I show you the probabilistic solution, you will still have my solution, which is you want to do the charming graph. Okay, we can do that at some point. Um, yeah, sure. Um, we'll do some new problems actually, which maybe are not in my book. Because that would be nice. Actually, maybe one last thing we should talk about with the union bound quickly, just to get a final feel of this, is that so you're given a tournament, um, and there are n people in it. Show that, like, for large enough n, I forgot the statement actually. Can anyone guess the statement from what I've said so far? Uh, uh, yeah. Oh, yes. At least so any subset of 100 vertices. Okay, I will just write it out. I've forgotten actually. Okay, show that there's some tournament such that for any subset S of 100 vertices, S subset of 100 vertices, there is some vertex um, in the graph such that uh, okay, there's a tournament and there for any subset of 100 teams there's a team that beats all 100 of them. So you construct the tournament. Sorry, I should have been more clear about this. So show that you can construct a tournament with some large number of people all playing with each other. So it's a round robin tournament. So that for any subset of 100 teams, there's someone who would have beat all 100 of those teams. What is n? We choose n. It's the number of people. Please repeat. Okay. So there's a round robin tournament. You have to design it. So imagine the IPL, right? Now in the IPL, obviously, like there's some teams which are like goated, like the RCB. There'll be no team that beat RCB. So we can't make it like the IPL. But imagine it were a more fair tournament, where people are maybe it's a bit more random. So and there's a lot more teams, importantly. Um, so like imagine that for every subset of 100 teams, there's someone who beat all of them. So inherently, there's no best team because you could just put the best team and 99 other teams, and there's someone who's beat all of them. So it's kind of this even out tournament and show that there you can design a tournament like this. Like there can be some results that happened in some big version of the IPL without RCB in it, importantly so that for every 100 there's someone. Yeah, people got very excited about RCB, I see. See, now you can't even say RCB has never won the IPL. It's crazy. Are you RCB fan? No, no, no. I was just, of course not. Why would I say all of this? True, true, true. Yes. Oh yeah, didn't they win? Okay, whatever. Let's focus.
For this, would
Um,
it be possible to like assign edges randomly and like for 2 to the power 100 or like something very large, you just win?
True, true. That is the exact idea in the entirety of this class. Think, don't overthink things. Just like pick randomly.
Yeah, like
Like
just
you
rush.
have n people, you need to decide who won. Just pick randomly. So that's the key observation that RCB is not in this tournament. So you can make it random. It's not deterministic. RCB doesn't have to win. Um, so for every pair of teams, A and B, you just decide who won randomly with 50-50. And then you check, okay, what's the probability that there's a subset S of 100 teams such that no one beat them all? So in particular, if I fix my subset S, so if I say, what's the probability that teams 1 through 100, no one beat them all? Well, there are n minus 100 other teams, and the probability that a certain team beat all of them is what? It's like half to the power 100. This is the probability that someone beats them all. So the probability that they don't beat them all is this, which is almost 1. But then the issue is this gets raised to another power of n minus 100. Because you need that the 101th guy didn't beat them all, and the 102th guy didn't beat them and all, and 103rd guy, and so on. Right?
Where
So
does
essentially,
that come from?
um, just think about it, right? So there are 100 people. What's the probability that the 101st team beat them all? It's half to the 100. They need to get lucky 100 times. So the probability that they didn't beat them all is 1 minus half to the 100. So the probability that no one beat them all is this to the power n minus 100 because there are n minus 100 other teams and no one should have beat them
Oh,
all.
I was assuming the team which beats them all is inside the set itself.
No, no, no. That wouldn't make sense, right?
Yeah,
Because
exactly.
yeah. Okay. So anyway, so the probability that this is bad, and we're going to use the word bad quite often in this class. So you have bad events, and we just define them like this. Um, and so it's this. And then you just similarly define the probability for every subset of 100 teams. So in particular, the probability that some 100 are bad is just the sum of all of these, which is like n choose 100 times this. Some constant, this is the constant number only, times n minus to the n minus 100. In fact, we can just take the minus 100 outside. So it's some d, something like this. Something. And the point is just this is polynomial, this is exponential, exponentials beat polynomials. So eventually this will become very small because c is less than 1. Whatever, you can think about it if you want. But the point is eventually for larger and this is less than 1. So you're happy. So yeah, the key idea with all of probabilistic solutions is don't overthink things. Pick randomly, check probability that something is bad, sum everything up, don't overthink it, prove that it's less than 1.
So there's a
Profit.
easier thing you can do for this problem.
Okay.
Take a tournament of 99 teams. Then every set of 100
Yeah, no,
teams.
the question
There are no
had
sets
at
of
least
100 teams.
101 teams. In fact it is written out. Yeah. That's a good one. Yeah. Yeah, you can also take tournament of 1 team by 99. Anyway, yeah, the question did say n is at least 101. Good catch. In fact, the IPL would work then, even though the RCB exists. We should find bound of n. No, we should not. Like, that is not an interesting job. Like, I am not interested in bounding this nonsense. Okay. let's now talk about expected values. And the reason expected values come up is because you can't always, it's not always a 0-1 scenario that some things are good and some things are bad. You might have more than just that. So let's say, for example, now this is a common this thing that again, this is a well-known problem. Prove that like we're going to consider a tournament where everyone played anyone and n people. Prove that there's some choice of victories you can make so that there are n factorial over 2 to the n minus 1, at least these many Hamiltonian paths. And a Hamiltonian path is essentially um, a series of people, A, B, C, and so on, so that all the people eventually occur exactly once, and A beat B, B beat C, C beat D, D beat E, and so on. A directed Hamiltonian path. Yeah, so undirected wouldn't make sense in a tournament because everything is joined to everything. So yeah. ODI World Cup 23. No, that's not true, right? ODI World Cup must not have had many. Would it have? Maybe it had.
She beat
I have a
everyone.
question. There is a chance there's a team. How can we confirm it? Yes, good question. So the CBSE way of thinking about probabilities helps with this understanding. Essentially, think of it as number of favorable outcomes by total number of outcomes. And if that probability is not one, so it's less than one, then there is number of favorable outcomes is not all of them. So there is some outcome which is like in the other set. So there is, okay, maybe another way of saying this is probabilities every 100 every group of 100 is good, is let's say positive. So let's say it's like at least is equal to 0.01. Let's say it's at least this. So the number of favorable outcomes is at least 1% of the total number of outcomes. In particular, there is some favorable outcome. So you're done. Imagine not using Bayes for this problem. Wait, how would you, why would you use Bayes? Like, there's no reason to use Bayes here. Okay. Yes, I agree frequentist probability is a scam. I just think it's an easy way of understanding it on the first principles. But there are, I mean, the more formal way is also basically saying the same thing because you have a bunch of events and you have a function from that to that. And if all of them map to the same thing, then it would just be probability equal one. Is it guarantees the probabilistic method will always work? No, of course not. If that were true, then it would be brilliant. But you know, um, in many problems, you will get a bound, which is you want to prove it's like linear, and you will get n to the n as the bound from probabilistic. So it will be extremely weak often. Um, and that's the interesting thing, that the same thing is true for greedy algorithms, that you will often get very weak bounds. But somehow they are the two most powerful methods in Olympiads, even though they're inherently very weak ideas in the sense that, a greedy algorithm in no sense needs to be anywhere close to optimal. Probabilistic method is literally taking things at average. So again, average case is nowhere necessarily close to optimal. But yeah. Ollie would have banned it, lol. No, I don't think Ollie would have banned it. Ollie would have just like grown out of combinatorics if that happened, because then people would just not find combinatorics interesting if everything was solvable with. Okay. I mean, the point here literally is, okay, again, pick randomly, but we're going to do one special thing, which is we're going to find the expected value of the number of Hamiltonian paths. Now, the other way we could have tried looking at this problem is find the probability that a certain path is Hamiltonian, and then summing over all of that, you can find the probability that some path is Hamiltonian or something. But now you don't want just one, you want a lot of them. So it's like messy, right? So in general, what you do is you find the expected value of number of Hamiltonian paths. Hamiltonian paths, in case someone is not familiar with this terminology, is just literally like a series of all the people in some order, so that the first beats the second, second beats the third, third beats the fourth, and so on. Number of Hamiltonian paths. And here we're going to use this magical thing, which is that it's equal, not even at most, it's equal to the expected value, is equal to the expected value that okay, maybe I'll just write it like this for now. In this case, this is true. This is not generally like something to remember. I will explain why this happened, but it's probability that like A1 to AN is Hamiltonian. So essentially, A1 to AN is like an ordering of the n people, and it's Hamiltonian if A1 beat A2, A2 beat A3, A3 beat A4, and so on. And the sum over all possible A1 to AN we are taking. And this is like not obvious. Why should the average value equal the sum of these probabilities? We'll explain that. But if this were true, then we would have that, okay, there are n factorial ways to order the guys, and there are the probability that this works out is half into half into half n minus 1 times, because there are n minus 1 things that you need to get lucky with. So it's, in fact, the expected value is exactly n factorial over 2 to the n minus 1. And then if the expected value is that, then there is some tournament which hits the average value. Is this because of linearity of expectation? Exactly. And we'll talk about how exactly that comes. You make the variables, the counter variables, indicator variables, I would say, but sure, counter variables also, I think, is valid terminology. Okay, anyway, so how we can claim something like this, the star is the key step, of course, is that with average values, expectations, we first need to, first of all, know how to define this. Maybe the definition was this, and then of course it would be true, but we don't actually know how you define it. So expected value of a random variable is defined to be the sum, and this is for a discrete random variable. Stop telling me that there'll be integrals and stuff. Like, I don't care. In general, you can do it over any measure if you just define. Okay, whatever. Probability, I will just do it for the integers into I. In fact, I'll do it for positive integers. Okay. And what this is saying, this is not a very true statement, but it's true for our purposes. It's saying that it's exactly what it's a weighted average of all the possibilities. For example, if X represented the roll of a die, then the probability that it's equal to 1 is a sixth, probability that's equal to 2 is a sixth, and so on. So the average value would be 1/6 into 1 plus 1/6 into 2 plus 1/6 into 6. Now, if the die were not like if it were not fair, that if, let's say, there was 100% probability that you get 6, then the average value is also 6. So you expect, as we would also get here, because you would get 0 into 1 plus 0 into 2 plus 1 into 6, because the probability of getting a 6 is 1. And so then the average value in this case would be 6, and the average value here would be 3.5. Yeah, in a discrete metric. So I mean, the more formal thing to do would be like write, instead of this, as like I belongs to image of X or something like that. And then you can sum. Anyway, and now the reason expected values are so brilliant is because they have this beautiful law, which is called the linearity of expectation. And essentially, that expected value is linear. And what does, first of all, this mean? What does this mean? What is the sum of two random variables? The sum of two random variables is essentially like you consider, first of all, what is a random variable? Just remind me, it's a function from the set of possibilities to let's say in this case, positive integers, right? And so is y. So x plus y is a function from the cross product. So let's say this is S1 and this is S2. S1 cross S2. So you basically see what happened in S1, you see what happened in S2, and then based on those two results, you add the relevant values and give the output. So, I mean, it sounds a bit strange, but essentially a much simpler way of thinking about it is, okay, you roll two die, and the first one, the average value is 3.5. The second one, average value is also 3.5. Then the average value of the sum will be 7. And that makes a lot of sense because these two rolls don't depend on each other. But even if I told you that, let's say that if I roll an even number on the first one, then I am, let's say, going to be more likely to roll an odd on the second or something like that. As long as at the end of the day, um, the distribution is the same, you will still be able to say this. So in particular, there's this sort of example of like the n people who wear hats and they pick a random hat. The n people in n hats, each of them has their own hat, but they might pick someone else's hat. You want to find the expected value of people who pick their own hat. Um, and the thing is that these things are not dependent. If the first guy picks his own hat, all the others are now slightly, I don't know, you can argue whether it's more or less, but there's some shift in the probability of whether the second guy picks his own hat. For example, if the first guy picked the second guy's hat, now the probability second guy picks his hat is 0. So it suddenly changes things. These are dependent events. Yet the expected value of the number of people. So, okay, so here's the trick which we use. Number of people who get their own hat is equal to, so we define x1 to xn, where xi is 0 if I does not get his own hat, and 1 if I does. So if you think about this, xi is a function. Xi is a function that maps possibilities to numbers. So xi is a random variable. And we're claiming that number of people who get their own hat is the sum of these random variables, which makes sense because if person 1, 3, and 5 got their own hats, then here 1, 3, and 5 would be 1, and the others would be 0. So the number of people would be 1 plus 0 plus 1 plus 0 plus 1, and so on, whatever. So essentially, there are n things that contribute to this number of people, and each of those things is either 0 or 1. And so so we can cleanly argue that the expected value of number of people that get their own hat is expected value of this sum, and we can split the sum into ex1 plus ex2 plus exn. And why this whole expected value thing is true, you can think about it. It's actually very easy to prove once you formally know what the definition of x plus y is. So I would suggest you go to Google, check the definition of x plus y, see if you can prove it on your own, else look it up. It's like a 3-line proof where
How
you
do you
just...
prove it for not discrete variables?
That's a good question. It's not... So, I mean, the thing is, you have to now define expected value for non-discrete variables. It's no longer a sum, it's an integral. And then the question is, what kind of integration are you working with? You should be working with Lebesgue integration because this is measure theory. And then a very similar proof to what you do in summations. Instead of swapping summations, you'll be swapping integrals. And the reason you can swap them is because there is some nice theorems which help us know that when everything is well bounded and everything, you can swap integrals. So it's almost the same idea, it's just slightly different implementation. Yeah, so anyway. So what happens here essentially is that expected value of number of Hamiltonian paths is the sum of these expected values of these indicator variables, x1 plus x2 till xn factorial, where each of these random variables is representing, so x1 might be 1 to n is Hamiltonian. Then this might be another. So essentially, there are n factorial different um, sequences of people, and the sum of those indicators should give you the number of Hamiltonian paths. And this is something to think about. It may not be entirely clear as to what exactly I'm talking about. You should think a bit about it. And then you can check that the expected value of x1 is exactly the probability that 1 to n is Hamiltonian, because it would be this into 1 plus probability of not being true into 0. That's how expected value is defined, like this. And it only takes value 0 and 1 when it's an indicator variable. So we get what we want. And so it's the sum of these probabilities, and so it's exactly this. And so the thing that helps us a lot is linearity of expectation. If you think about it, every proof we have written with union bound can be rewritten with expected values because of linearity of expectation. And the reason for this essentially is that essentially you can think of the expected value of number of bad pairs as at most as equal, in fact, to the expected value that of these indicator variables or something, where x1 is that 1 to k is bad. If 1 to k is bad, it's 1. If 1 to k is not bad, it's 0, etc., something like that. And then you can show, and then the sum is going to turn out to be exactly the sum of these probabilities, which we showed is less than 1. So you show that the expected value of number of bad things is less than 1. So there's some scenario where if the average value of something is less than 1, then in some scenario it's going to be 0. Am I tripping, or is this video lagging? That's my bad. Give me a second. Probably because my laptop is low on charge. Can you guys hear me though?
Yeah.
Yes.
Okay, cool. Yeah, I will just turn off camera for a little bit, but once this thing is charged a little bit, it should be fine. Okay. Yeah. And so let's do one interesting yeah, I'm just wondering what's the best thing to do with this now. Okay, let's pick a random problem from my book, which is a problem section, ideally. Okay.
The previous slide, we did that with probability, right? How are we sure that it's going to work? If it was expected value, then it makes sense. But how does it work for probability?
So think about the definition of expected value, right? It's the sum of these things. And now if the probability that x equals 0 were 0, the probability that the number of bad events is 0, then essentially your sum becomes something that I is at least 1, probability of something into I, or something like that. And then all of these i's are at least 1. So it's some weighted average of positive numbers, strictly like positive integers. And any such weighted average will be more than 1, at least 1, at least, I should say. Right? Because if you take the weighted average of 1, 3, and 7, then that can't be less than 1. So if the expected value is known to be less than 1, then the probability that x equals 0 must be non-zero. And so then we can go back to the original argument. So we can say that the number of bad events in some cases equal to 0.
Okay.
Does that make sense?
Yeah, it does.
Okay. Yeah, I would suggest that like if people have access to like my book in any way, like read things up there, because this is meant to be more as like an advertisement sort of thing for probabilistic, but you can obviously learn a lot more and a lot more formally and rigorously if you just read carefully in that. And I think it'll be good if you're left with some questions today and you're not very sure about how something happened, because that gives you more time to explore. Okay. So what I was going to do is, we've kind of run out of time almost. So I am going to go back to this. If you do not want to see the proof, in fact, I'm not even going to tell you the full proof because it's a bit like too crazy, but I'm going to show you the key idea. If you don't want to listen to it, you can choose to leave or mute or whatever you want. But also there are multiple proofs, so you can always like find my proof even if I show you this one. And the magic thing is, so what are linear functions G? Linear functions, as we said, are functions of this form, a dot x. And so we consider this random quantity, ma, to be the expected value of, and this is a bit crazy, fx minus a dot x. So if fx were linear, then there is some a for which ma is like 1, because for that, then fx minus a dot x would always be 1, because fx is equal to a dot x, would always be
Is this
0,
the
sorry.
same A as above?
I mean, it's for every, like a is a vector in f2 to the n, like it's
No, like
some 0, 1
f of
sequence.
x1 up till xn is equal to A
No,
dot
this
x.
is not true. This is what we would like. This is what it means for a function to be linear, if
Oh,
there is
okay,
an a such that this is true. So if this were true, then the probability of this would actually be equal to 1, because
correct.
you would always get linearity. So I guess what you can say is this is true for G, because G we have to construct always to be linear. So then I guess it would be fine. But so A is not yet defined. A is just something. And if F were linear, then there is some choice of A for which the expected value becomes 1. 1 for some A if linear. And what we need to show in particular in this problem is not this, but that fx is equal to gx for most values. So in particular, gx is basically a dot x for some a. So fx minus a dot x is 0 for most values. So in fact, if you do the computation, you have to show essentially that this is at least 1 minus 2 epsilon or something like that. Or maybe 2 c epsilon. Some like 1 minus some constant times epsilon. You have to show this. So essentially, you have to show there exists a such that ma, the expected value of this quantity is at least 1 minus c epsilon. And don't worry too much about the details, and don't worry too much about where this came from. I'll talk a bit about that, but just believe me for now. And now what you do is you find the expected value of ma itself. And the expected value of ma, if you can show that the average value that ma takes is like close to 1 minus c epsilon, then there is some choice of a for which it does take the value. So you're taking expected value of a quantity that depends on expected value. But if that were not crazy enough, actually this expected value is too hard to calculate and you cannot do it nicely. What you can calculate nicely is the expected value of the cube of this quantity. And at this point, you're probably questioning life. But the reason cubes come up is because, like, then you will have fx, fy, and fz, and then you can start using this property. Because if z was equal to x plus y, then things would cancel out and things would become nice, etc. And if they were not, then also things would cancel out, etc. So you can find the expected value of the cube of this quantity. You can find the expected value of the square of this quantity. And then you claim that okay, if the average value of the cube is, let's say, 100, and the average value of the square is only, let's say, 20, then there is some choice for which the value is at least 5. Because if it were always less than 5, then going from squaring to cubing can't take you by a ratio of more than 5. And so then you show that this by this is at least 1 minus, I think, 4 epsilon or something like this. And so you have some choice of A for which MA is at least 1 minus 4 epsilon. And so you're done. And I've not actually shown you how to compute these things, but there is like, it's only like 2-3 lines of computation actually. It's just a bit complicated and not very interesting. The thing that I was amazed by this proof is just the fact that you choose quantities and you choose to cube them and square them and work with expected values in these beautiful ways. And this is a pretty crazy solution. I actually don't fully understand the motivation that Kevin had for the solution. I think my solution is a lot more intuitive. Anyway, so but the thing I want to point out with this is that a lot of times, so far, everything we saw, there was no difficulty in how to pick the things randomly. As in, like, like in this tournament, what do? You just decide whether A wins or B wins randomly with 50-50. There's no inherent difficulty in that step. The difficulty is either in realizing you should use probabilistic or in doing the algebra. Um, Similarly, here, if you want to show at least these many Hamiltonian paths, you just find the expected value of number of Hamiltonian paths. But sometimes in some very difficult problems, the difficulty can be in choosing the right quantity to find the expected value of. And once you choose the quantity appropriately, everything will fall into place. And here, choosing this quantity of MA was like probably the hardest step of the solution. And yeah, I mean, this is meant to be less of teaching you this, more of like showing you that magic can happen with these kind of tricks. Anyway, so I guess one thing to see maybe later, I didn't show it much today, is this technique of alteration, where you find the expected value of some quantity while some things might not be good, and then you alter the thing. That's also there in my book, so you can read that up. And yeah, but I think the thing to know about probabilistic is when you're unsure about what to do, just pick randomly. That's the philosophy. And use linearity of expectation, use the union bound. Those are our two most powerful tools. Those are the two main tricks. But yeah, I guess I will stop sharing. There's some chat questions, yeah. Anything here? Okay, people are talking about something. When you're unsure, just pick randomly. Indeed. I will stop recording.